It's Friday? So I don't know if you're aware of that, but today marks the halfway of the semester. Huh? That should have been a long time ago? What do you mean, you're not having fun? Yeah, so today's the, I guess, this week was the 8th week, and since there's 16 weeks in the semester. Okay, do you have any questions?
Yeah.
Yes.
14.
On 3.3, right? Okay. We have y equals the natural logarithm of quantity x to the 4th times sine squared of x. So, as we have to do for pretty much every single problem in this section, we're looking for the derivative in terms of y, of x. So, what should this scream when we look at it? Chain rule, right? We have ln of a function, so it would be 1 over x to the 4th sine squared of x. Of course, another thing you can do is you can actually break this apart into two logarithms, take the powers out, and do it that way. So let me do it in this fashion first, and then I'll show you the other way as well. So this is 1 over the function times the derivative of the function. So if you look at your function, it looks like a product of two functions, right? So you need the product rule. So it'll be 4x cubed times sine squared of x plus. Now what is the derivative of sine squared? Two times sine of x cosine of x times x to the 4th. It is sine of x quantity squared. So the first thing we need to deal with is the square part of the derivative of the function. Does that make sense? Okay. Otherwise, as I said, y is 4 ln of x plus 2 ln of sine of x. And so dy over dx then will just be 4 over x plus 2 times cosine of x over sine of x. Does that make sense? And I guess you can kind of see it if you want. Think about this here and actually distributing. You're going to have 4x cubed times sine squared divided by that. You end up with 4 over x. And then you look at the second part divided by that, and you'll end up with that. Since the x to the 4ths cancel out, you have the 2, and then 1 sine with the sine cancels out. Yes?
Well, confused how we got 2 cosine x without that sign.
The derivative of ln of a function is
1 over
f prime over f, or g prime over g. So, derivative of ln of g of x is g prime of x over g of x, or 1 over g of x times g prime, right? So if it's confusing, then this, think about this as 1 over sine times cosine. Okay? What else? Anything else? Yes.
Did you do number 16?
Number 16?
It's big and messy.
But it doesn't have to.
Oh. My answer is big and messy. I don't know if I should simplify it.
G of u is equal to the natural logarithm of the square root of 3u plus 2 divided by 3u minus 2. So obviously, if we want to get creative here and we start taking the derivative, you'll have 1 over the square root times the derivative of the square root, which could be quite fun. So alternatively, you can notice that that is equal to ln of the quantity 3u plus 2 divided by 3u minus 2 to 1/2. So it's equal to 1/2 times the ln of 3u plus 2 over 3u minus 2, which equals 1/2 ln of 3u plus 2 minus 1/2 ln of 3u minus 2. Less ugly.
Yeah, that was a lot easier.
Right? So now when we look at g prime of u, it'll just be 1/2 times 3 over 3u plus 2 minus 1/2 times 3 over 3u minus 2. And as it turns out, you can actually combine these and you can come up with something very nice. It's just minus 6 over 9u squared minus 4. Yes? The derivative of 3u plus 2?
Oh.
Does that make sense? Do you see that last part? Or not really?
So, my denominator is now 2 times 9.
Well, forget about the 1/2s.
Okay.
Right? You have 3 over 3u plus 2, 3 over 3u minus 2. Least common denominator is 9u squared minus 4. Right? Difference of squares. So you end up with, and again, actually forget about the 3 for a second as well. So think about the 3/2 on the bottom. You'll have 3u minus 2 minus 3u minus 2. So the numerator is just going to be minus 4.
Scroll up a little bit. Right there.
So let's make it a box. Is that making sense? Okay, what else? $20. What's the problem with 20?
Like, I'm just having problems figuring that out. I ain't get the right answer.
It's a quotient, right?
Yeah.
So you need to apply the quotient rule to the derivative of the first, which is they must really like to clean at 9:30 in the morning on Monday, Wednesday, Fridays. Okay. So again, the derivative of the top is
E to the x
okay.
times 1 plus x.
Okay. Minus.
E to the x all over 1 plus x squared.
Okay.
Why you told me that was wrong?
Well,
That
maybe because the next step is to actually simplify things.
simplify that?
Yeah, v to the x plus x times e to the x minus e to the x. So the e to the x is cancelled out, so you're left with x times e to the x over 1 plus x quantity squared. Does that make sense? What?
Oh wait, okay, so the e to the x is cancel out. Now we have 1 plus x all over 1 plus x squared. Right? Oh.
So what you're telling me is that
Oh,
x...
wait, no. I know I did wrong here.
I'm saying e to the x times 1 plus x minus e to the x.
Yeah.
So how do you cancel them out?
I got it.
The first thing, you have to distribute e to the x. Right? So when you distribute it, the only thing you're left with is x times e to the x. Because the e to the x is cancelled out. Does that make sense?
Okay, that makes sense.
Yeah?
Yeah, I got it.
Okay. What else? Okay. Again, what is the problem? Because you're also looking. You're again looking at a quotient rule, right? What is the derivative of the top? Maybe that's the problem.
Yeah, I'm getting negative e to the x minus x e to the x.
Okay.
Minus 1 plus e to the x times 1 minus x e to the x.
You forgot to multiply the denominator. We have 1 minus x e to the x divided by x plus e to the x. So when you look at f prime, you have minus e to the x minus x e to the x times x plus e to the x. Minus 1 plus e to the x times 1 minus x e to the x divided by x plus e to the x quantity squared. Right? Right?
Okay, I see what I did.
And now the next step would be to actually multiply them out, because when you multiply them out, things will cancel out. Notice that you have x times e to the x squared, and then you have x times e to the x squared here as well, so they'll actually cancel out. By the way, out of curiosity, what is e to the x times e to the x? E to the 2x and not e to the x squared. Alright? Laws of exponents. You add the exponents, you don't multiply them. Alright?
Wait, how does it simplify again?
Well, what happens when you distribute? Or I'm sorry, not distribute. I don't want to confuse you. FOIL.
You mean the numerator?
Yes. What do you get? You get minus x e to the x minus e to the 2x minus x squared e to the x minus x e to the 2x minus 1 plus x e to the x minus e to the x plus x e to the 2x, all divided by x plus e to the 2x quantity squared. And this is what I was saying, x e to the 2x cancels out, moreover minus x e to the x plus x e to the x cancels out, so we're just left with, I'll take a minus out in front, we have e to the 2x plus e to the x plus x squared e to the x plus 1 divided by x plus e to the x quantity squared. And again, I'm hoping that everybody knows that e to the 2x plus e to the x is not equal to e to the 3x or some combination of that. Yes?
Or
Sure if I say so?
Right, you know how you crossed out some stuff on the numerator? Do they actually cancel, or are you just adding them together?
You add them together and they end up to be equal to 0. X e to the x minus x e to the x is?
Oh, okay.
Okay? Wonderful. What else? Anything else? Or am I to assume that nobody else actually attempted the homework? That's what the weekends are for? I see. Okay. Alright, let me see. How about last time we talked about all this stuff, and before I start off with new stuff, I just want to quickly look at one thing. Actually, we did 57, right?
Yeah.
So then I guess we've done pretty much everything. Okay. Okay, so then let's move on. Today we're going to talk about exponential growth and decay, which you've probably seen before if you've taken like a chemistry class. One of the things that we're going to learn later on in the section is exponential decay, and for instance, one really big application of that is carbon dating. So that probably you've seen in chemistry. But before we get there, I guess one of the things we're going to do before we get there is actually see the logistics behind it, as in how do you actually have those particular types of equations, because you've probably seen, as I said, equations involving exponential growth or decay for that matter, but you were just given the equation and say this is the equation that governs growth or decay, without actually telling you why that's the case. So we're just going to look at it quickly. So it all stems from something called differential equations, and we're going to touch on differential equations at some point. Well, actually, no, we're not. I got confused. That's actually in Calc 2. Well, this is basically the only time we're going to see differential equations right now. But the idea is the following: dy over dt is equal to k times y is called the law of natural growth. I'll write it as slash decay, depending of if k is positive. If k is positive, you get growth. If k is negative, you get decay. And the idea is, this is actually observed in real life. The idea is that the rate of change is proportional to the size of the population. Okay, that's basically what it says, right? Remember, the derivative is the rate of change. So if y of t is a function of time, is your size of your population of time t, what this equation says is that the rate in which the population grows is proportional to the size of the population, which would make sense, right? Does that, do you understand what basically we're trying to get at? Clearly, the larger the population, the better chances of, the growth actually being, you're going to look at the proportion versus the size of the population, right? If you have 5 people, chances are they're not going to grow as fast as if you have, 1,000 of them, right? Does that make sense? Okay. It's relatively a very simplistic model, and mathematical modeling is actually a very large area of study in mathematics, and this particular equation is relatively nice, but it's not necessarily very accurate, because what it doesn't take into account is what happens if the population gets too big. Like, for instance, Earth at some point in the future, if you're actually trying to use this to model the population of Earth, of people, at some point you'll end up actually, we're actually going to have to start living on top of each other's heads because we're not going to have enough space anymore to live. So,
How long will that be?
actually, if you use this particular model, probably not more than like 50 years.
Like we'll all be dead.
But clearly, see, the one thing that this doesn't take into account again is the food supply. It doesn't take into account the death rate. It doesn't take into account the actual surface of the Earth and everything else. So anyway, but for many reasons, this is actually very useful. So how would we solve something like this?
Wait, what are we solving? We have to
Well, by the way, this is called the differential equation. And why is it called differential equation? Well, remember, differential just means the derivative, right? It just says it's a differential equation because it's an equation involving your function y and its derivative. Okay? So our goal is from here, from this equation, the goal is to come up with the actual function, which should be very easy to do. Why? What is this saying? This says that if I take my function, its derivative is just some number multiplied by the function, right? Which of the all derivatives that we've ever talked about, when you take the derivative, your function stays the same? Exponential functions, right? So that basically says that our guess is that y of t is an exponential function. As it turns out, we can do actually more than that, and we can actually say that the general solution for dy over dt is equal to k times y is y of t is equal to y of 0 times e to the kt. And this is the logistic model for the population growth, for the population function. Does this make sense? If you forget about the y of 0 for a second, think about the derivative of e to the kt. It'll just be e to the kt times k, right? Which means the derivative will just be k times your function, right? y0 just basically takes into account, this is your initial population. That's what we talk about. Yes?
Wait, where's the e go? Like when we take the derivative of e to the kt, we get e to the kt.
Okay, what's the derivative of y prime? I mean, what's y prime? Y of 0 times e to the kt times k, right? What is this? This is y of t. So this says that dy over dt is equal to y times k, which is our differential equation.
Okay, so y takes into account the whole e. Right?
Well, that is y. This is your function.
Okay. So y just stands for the function, and then when we look at that function, e is the function. Okay.
It's part of the function. Okay. So should I go through this example, or maybe we should just pick a problem from the book? Let's just pick a problem from the book. How about I do number 3, problem 3 on page 173. So let's see. A bacteria culture initially contains 100 cells and grows at a rate proportional to its size. So this first sentence tells us what? It tells us the initial value, but moreover, it tells us that it grows at a rate proportional to its size, which means the bacteria culture will satisfy the exponential growth equation. Does that make sense? Okay? So that means that y of t is going to be equal to y of 0 e to the kt. Right? So now do we know what y of 0 is?
Yeah.
100. Bless you. After an hour, the population has increased to 420. So how should we express that in terms of our equation? Sorry? T would be 1. So y of 1 will equal 420. Right? Does that make sense?
So y of 0 is the initial.
Basically what we're saying is, maybe I should have written this all along. Y of t is the population size after at time t. So if you talk about initial population, you're talking about t equals 0, right? Because that's when your time starts, basically, right? Okay, part A. Find an expression for the number of bacteria after t hours. So part A asks us, what is y of t? So let's make this interactive. How would you guess we would do that? What do we need? We need to find out what k is, right? Because we know what y0 is, or y of 0 I should say, right? So how can we figure out what k is? We have that y of 1 is equal to 420, right? So what we know is that y of t is equal to 100 e to the kt, right? And we also know that 420 is equal to 100 times e to the k times 1. Right? And so, let's see. 4.2 is equal to e to the k. Right? Divide 420 by 100. And so k is just the natural logarithm of 4.2. Make sense? Okay. I don't actually have a calculator to compute what that is, but our answer says that y of t is equal to 100 e to t times ln of 4.2. Right? Does that make sense? Now keep in mind, e and ln don't cancel out. Everybody sees that? Why? Because we have that t. If you do want to cancel them out, and I'll give you, we're not going to use this notation, but I'll give you this alternate notation. This is equivalent to saying it's 100 4.2 to the t power.
Yeah, that's the normal equation, right? Basic.
Well, you moved in the t in the exponent of ln. What is it called? I forgot. The butterfly effect. Right? And now e and ln can cancel, and you have 4.2 to the t power. Right? But in reality, what people do is you just actually take a calculator, and we actually compute this ln of 4.2, because it kind of gives you an idea of how fast your population is growing. That is your growth constant. So you can kind of get a feel for how large it is. And as it turns out, it's actually very large, because ln of e is 1, e is 2.7. So this is well over 1, which means in an hour your population will for sure double, if not, a lot more than that. Okay, well, we are talking about bacteria, so, Okay, part B. Find the number of bacteria after 3 hours. T equals 3, so we're looking for y of 3, right? And I'm sure everybody can put it in and figure out what it is, right? Okay? Yeah, you're going to need to use a calculator for this. And it won't be on the test.
You just plug in 3 for Keith?
Yes.
Okay.
Find the rate of growth after 3 hours. I guess I could technically ask it on the test. All I have to do is just say, leave it in, in these forms.
That'd be easy.
So we'll find the rate of growth after 3 hours. Well, what is the key word? Rate of growth.
It's not a constant.
Rate means the derivative. So we need to figure out what y prime is and plug in 3. Does that make sense? Now, you can do that, or you can be sneaky about it. So we could actually compute y prime of t, right, dot, 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 plug in 3 and work out. However, this is a exponential growth formula that says y prime of t is just k times y of t. In part B, we computed y of 3. So in part C, it's just going to be y of 3 times k. Do you see how you can be sneaky about it? Okay. Part D. When will the population reach 10,000? So we need to figure out what t is, right? In the equation, 10,000 equals, I don't know what I'm writing here. 10,000 equals 100 e to the ln of 4.2, and I'll multiply by t, right?
What's the question asking again?
When will the population reach 10,000?
And then we solve for t.
And as it turns out, it'll be in about 3.5 hours or so.
Boy, so we divide by 100, and then we log each side.
Yes. It'll technically be a ln of 100 divided by ln of 4.2, right? Now, how did I say it's going to be in about 3.5 hours? How did I figure more or less that's going to be the case? The idea is, as I told you, this is equivalent to saying 100 equals 4.2 to the t. Now, if you ignore the 0.2 for a second, 4 squared is 16, 4 cubed is 64, right? 4 to the fourth is 256. It's well over 100, right? So, as soon as you get past 3, this number will basically be very close to 100, right? Kind of like the ballpark idea, which is what I said all along. Because k was so big, your population will grow very, very fast. Okay? Is this making sense? Okay. How about exponential decay? So exponential decay shows up quite a lot, as I said, especially in chemistry. I don't know how many of you actually took chemistry. I don't know if you watch any of these like shows like on the History Channel, or if you watch like Bones on whatever channel that is, Fox. How do you determine how old is a set of fossils? Do you know?
Like some kind of carbon.
It's called carbon dating. Do you know what it actually does? Each radioactive substance has a rate of decay that's already fixed. And so there's something called the half-life of a radioactive substance. And so based on that, you know if it's a human, you know the amount of carbon that the human was supposed to start with. And so you measure the amount of carbon that's left in the body, and you can figure out how long it has passed since the person has died. And so that's basically why radioactive decay is actually very used in real life applications. So let's see, let's call it, I guess they use m. M of t is equal to m0 e to the kt, and in this instance k is less than 0. They're using m because in general you're talking about masses, which means you're talking about the amount, weight. And so we're looking at m as being, so m of t is the mass after time t, or at time t, I guess. Okay, so I'll skip example 2 since you've seen that before. Actually, no, let's do that before. Would you guess what the half-life of a radioactive substance? So the question is, after how long is the mass of the substance half? So how should we figure it out? And this is more or less theoretical at this point because we don't actually know what the rate of decay of the substance is. So obviously our answer is going to be in terms of K, right? But how can we figure out what the half-life is going to be?
0.5.
So half-life means the substance will be half its mass, right? So we need to find T so that m of t is 1/2 of m0.
What does the M0 mean again?
The initial mass.
But this is for decay. Initial mass of the decay, right?
Well, before we talked about populations. In general, that's kind of like the convention. Whenever you talk about growth, you talk about populations. Whenever you talk about decay, you talk about masses. That's just because those are the two things that happen in real life the most. Exponential growth shows up the most in populations, and the decay shows up in, like as I said, radioactive substances because they decay in time.
So why the zeros for growth, if the zeros for decay? Is that,
But again, this is just notation. Okay, so how do we figure this out? Well, we're going to have 1/2 m0 has to equal m0 e to the kt. Right? m0's cancel. E to the kt is equal to 1/2. Means kt is equal to ln of 1/2. But that is the same thing as minus ln of 2. And so t is just going to be minus ln of 2 divided by k. And notice the key idea behind this is that we found the half-life of a radioactive substance without actually talking about what the substance is, what is your initial mass, or anything like that. The only thing that we don't know is the rate of decay. So once you're given the rate of decay, then you can figure out exactly how long it takes for the substance to get to half of its size. Is that making sense? Okay. Let's look at a problem, I guess. Where are decay problems? What do you have to do? 8? Okay, how about problem number 9? Should be simple enough. And the reason why I'm giving you this, the reason why I went and I actually did this particular formula, it'll become apparent as soon as we start talking about this particular problem. It says the following. The half-life of cesium-137 is 30 years. So cesium-137 has half-life of 30 years. Suppose we have 100 milligrams sample. So what does that tell us? M0 equals 100. Right? First question is, find the mass that remains after t years. So what is m of t? And this is where the half-life comes into play. Half-life is 30 years, right? So if you come from this formula, that formula tells you that k is going to be minus ln of 2 divided by 30. Right? Does that make sense? Cross multiplying k and t can switch around, right? So maybe I'll just write it here as well. Another formula says that k is minus ln of 2 over t. Right? Does that make sense? Think about coming back here, and instead of solving for k, you solve for t. So you end up with minus ln of 2 divided by k instead of divided by t. Right? So that's basically part A, right? M of t is equal to, well, whatever that number is. Anybody has a calculator? Since it just looks ugly. Sorry? Negative ln of 2 divided by 30, yes. So negative 0.023 times t. Good enough. Is that making sense? Okay. Part B. How much of the sample remains after 100 years? Would you know how to guesstimate, by the way? Obviously, we're looking for m of 100, right? But would you have any idea how much it is? Without actually you doing any sort of math. I mean, any sort of actually putting it in. In 30 years, you get half. So you started with 100. In 30 years, you end up with 50. In another 30 years, you end up with 25. In another 30 years, you end up with 12 and a half, right? That's after 90 years. Another 10 years will give you basically, instead of a half, it'll give you a sixth, right? It'll decay, roughly speaking. Obviously, I'm assuming that's linear, which is not the case, but nonetheless, you know, I'm saying just kind of like in the ballpark of what you're looking at, right? So basically, you're going to be looking at about 10 grams, 10 milligrams, right? Is that making sense? This is sometimes what I've been trying to tell you is when look at a test in general is if you spend a couple of seconds kind of figuring out what you're actually trying to get at, it might be easier to realize if you actually did the problem correctly or not, right? So when I would think about this before I actually put in the numbers, I would kind of like figure out, well, what is actually my expectation? You know, that's basically anyway. After how long will only 1 milligram remain? So what do we need to do here? We need to figure out what t is, right? It's because it says after how long. And what do we know? 1 has to equal 100 e2 minus 0.023 times t. Right? And I'm assuming you can all solve for t from here? Yeah? Yes?
So doing our homework, how far do you want us to go?
Oh, you actually have to figure out what the actual number is. So, basically the idea is that e2 minus 0.023 t is equal to 1 over 100. So minus 0.023 t is minus ln of 100. Well, it's ln of 1 over 100.
No. I got a little confused as to how previously you said ln of 1 over 2 equals negative ln of 2.
Because this is the same thing as ln of 2 to the minus 1.
Oh.
Or it is the same thing as ln of 1 minus ln of 2. And ln of 1 is 0. Right?
Oh.
So it's the same argument here. It was 1 over 100. So ln of 1 over 100 is the same thing as ln of 1 minus ln of 100. So just end up with minus ln of 100. So t is just going to be ln of 100 divided by 0.023. Actually, let's finish this problem off. Can you tell me what that is? Well, give me the actual number. 200.227. Okay. 2247. Okay. Okay. Let's play a game because I want to see if you actually do you know how to figure this out? Can you tell me it's 200 years and how many months? Would you know how to figure out how many months? 0.2247 times 12. Is everybody understanding this? There's 12 months in a year. We're looking at a 0.22 of a year, right? So that will give you an idea about how many months, right? It'll be roughly about, I guess, I don't know, 2 months, 3 months? Roughly about 3 months, I guess. Does that make sense? Obviously I could ask you in how many days, but that doesn't really fly, right? Considering we don't know how many, months don't have the same number of days. All the months.
We can give you days without the months. We can give you days without the months, right?
Yes, well you can try and convert all that, well, yes and no. How many,
Days are in a year.
how many leap years are you going to have in 200 years? That was funny. Okay. All right. Yes.
Can you just fix that by putting 365.25 days per year?
Technically, but yes and no. I mean, again, there's some law of averages over there because, I mean, you got to think about the fact that depends on what year you're starting and how many years you have. If you have a multiple of 4, then yes, 365.25 I guess would work. But what if you don't have a multiple of 4 years? And if you, let's say this year is a leap year and you finish off with a leap year, then you actually have an extra. Anyway, not worth the actual effort. Okay. Newton's law of cooling. Anybody remembers the Newton law of cooling? It says that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, assuming that the difference is not too drastic. Okay? How would that be actually written in terms of our equation? It says the rate of cooling of an object. So if I denote with T, capital T of T, the temperature of the object at time T, then the rate of cooling of the object would just say d capital T over dt, right? Is equal to, is proportional to the temperature difference between the object and the room, right? So proportional means K times the difference between T and TS. They're using TS, so TS is room temperature or environment temperature, I guess, right? Does this make sense?
So far.
Okay, now how would you solve something like this? And as it turns out, it's exactly the same way as we had the previous problems. So if I do a substitution, if I let y of s be equal to, or y of t I should say, not s, equal to capital T of t minus capital Ts, then can you tell me what dy over dt is? It'll still equal d capital T over dt, right? Since Ts is a constant. Does that make sense? Moreover, my original equation will just become dy over dt equals k times y, which I know how to solve because I solved it. Right? Is this making sense? So it looks exactly the same as before. So let's apply this to a problem and see how things work. So, I mean, Sunday is going to roll over. You're going to have, I guess, football, and 2 hours before football starts, you just open up your fridge and realize you're out of beer. So you go and buy beer. You really want to know how long the beer needs to be staying in the fridge to reach the proper temperature to be able to drink it, right? I mean, of course, unless you buy Coors Light and it has the, the mountains that, turn blue nowadays, how would you figure that out? I mean, of course, you can, take them out every half an hour or so, stick your tongue to them and see if it sticks. But I mean, you have the mathematical tools to figure that out. Right? I mean, real life problem. Okay? So, I guess I probably could have had that written out as an actual problem, but oh, actually, you know what? Example 3 works perfectly. They say, but a soda pop, but we can use it. We can assume it's beer. So, a bottle of beer at room temperature is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. By the way, is anybody here a fan of MythBusters? Have you ever saw that show about how you can cool faster? A 6-pack of beers. And it turns out actually ice and salt works the best. And it actually worked even better than using nitrogen, liquid nitrogen.
I think salty ice.
Not that much. The key idea is as soon as you put salt into the ice, what happens is it actually lowers the temperature of the ice. It actually goes well below freezing because of the properties of the salt, of the sodium. And so it actually gets lower than 32 degrees, or not 32, whatever it is. The temperature of ice, I think, is like 12 degrees or something, right? So, but anyway, okay. So, a bottle of beer at room temperature 72 degrees is placed in a refrigerator where the temperature is 44 degrees. After half an hour, the beer has cooled to 61 degrees. What is the temperature after another half an hour, and how long does it take for the bottle to cool to 50 degrees?
What number is this?
This is example 3. Since I talked about beer, this is the only one that actually talks about cooling it. The other ones actually talk about, if I'm to actually do a problem from the book, I don't know, I mean, I don't have to do this since it's an example. I can do a problem from the book, which actually says the exact opposite. Take a bottle of beer from the fridge, put it in the room, after how long it reaches, the certain degrees. So it's going to be warming instead of cooling. Would you like me to do that instead? Nobody wants warm beer, yes, but nonetheless. So which one? Warming it up? Okay. That was problem 15. It's going to be in Celsius degrees though, so you know, bear in mind that's different degrees. When a cold drink is taken from a refrigerator, its temperature is 5 degrees Celsius. After 25 minutes in a 20 degrees Celsius room, its temperature has increased to 10 degrees Celsius. What is the temperature of the drink after 50 minutes? When will its temperature be 15 degrees? So, we're going to basically have to figure out how to solve the problem. So we need to find our actual model, right? So let's set up the differential equation. How is the differential equation going to look like? So what do we know? A cold drink is taken from the refrigerator. Its temperature is 5 degrees Celsius, right? How is that going to be related in terms of capital T? So again, let capital T of T be the temperature of the, let's call it beer, at time T. And yes, you might say, who wants warm beer? But that's exactly the point. The question is, what if you taken out, beer, and then all of a sudden you had to go out of the house and you came back half an hour later? Do you still want to drink the beer, or is it too warm by now? You can be creative with these things. Okay, so how is the fact that the temperature of the cold beer is 5 degrees Celsius?
T of 0.
Capital T of 0 is equal to 5 degrees, right? Very good. What else do we know? After 25 minutes in a 20 degrees Celsius room, its temperature has increased to 10 degrees Celsius. How should we write that down? So first of all, because the problem says 25 minutes and then it asks us about 50 minutes, we should set T to be minutes. Right? Does that make sense? Before we talked about hours, but it only makes sense to talk about minutes, because otherwise 25 minutes, 25 over 60 of an hour, that's not necessarily something that you really want to be, playing with, right? So how do we set the other things up? What do we know? Yes? T of S is equal to 20 degrees. And what else do we know? After 25 minutes, the temperature has increased to 10 degrees. So T of 25 equals to 10, right? Okay, so now what is our differential equation? dt over dt is equal to k times t minus 20, right? Does that make sense? So the way we solved this in the past, or I showed you how to solve it, is we denote y of t to be capital T minus 20, right? Yes?
How do we get T of S again?
It tells you that the room is 20 degrees.
Okay.
Remember, TS is the temperature of the environment?
Initially, or?
That doesn't change.
Okay.
Assuming, not 50 people go in the room. Okay? Or, turn on the oven and forgot about it. Okay, so, how do we set this up? Well, clearly, if y of t is equal to t of t minus 20, then our differential equation is just dy over dt is going to equal k times y, right? The solution of this differential equation is y of t is equal to y of 0 times e to the kt, right? Does that make sense? Okay? Bless you. So now, can you tell me what y of 0 is? We need to figure out what k is, right? That's basically our goal. So can you tell me what y of 0 is? That means t is equal to 0. But remember, y of t is defined to be t minus 20. So it'll be t of 0 minus 20, so it'll be 5 minus 20, so it is negative 15. Right? Okay? What else we're given? We're given that t of 25 is equal to 10. Right? Or should... Okay, let's do that. So can you tell me what y of 25 would be? Or should we compute directly capital T of t? Maybe we should do that. Before we do this, can you tell me what capital T of t would be? From this box, it's going to be y of t plus 20. Right? So it'll be capital T of t is going to equal 20 minus 15 e to the kt. Does that make sense? Yeah? So now all we have to figure out is what k is, right? Basically all this brought us back to problems we did with exponential growth and exponential decay, right? We are given the initial value, we came up with the equation, we plugged in whatever other value here, and we came up with the value of k, right? So in exactly the same fashion, this will work. So we're given that t of 25 was equal to 10, but t of 25 is equal to 20 minus 15 e to the k times 25. Right? So from here, 15 e to the k times 25 is equal to, so this is going to equal to 10 over here. So it is equal to 10 e to the 25k is equal to 10 over 15, which is 2/3. So 25k is equal to natural logarithm of 2/3. So k is 1 over 25 times natural logarithm of 2/3. Does this make any sense? Oh, well, I solved for 15. So what I did is I moved this term to the right hand side and 10 to the left hand side. So you have 20 minus 10 gives you 10. Okay? Does that make sense? So after all of this work, you might be inclined to just do the tongue test to see if it's cold enough or not. Okay. So what is the temperature of the drink after 50 minutes? Clearly you put in 50 minutes, right? So you're looking at T of 50. We already figured out what K is. I mean, it doesn't look pretty, but that's basically what K is, right? And you can compute it to figure out exactly what the value is. It'll be a relatively small value, because ln of 2/3 is less than 1. And okay. So, by the way, would you be able to tell me what would you guess the temperature would be after 10 days?
Yeah.
20 degrees, the temperature of the room, right? Right? By the way, notice that K is less than 0. Do you see that? ln of 1 is 0. 2/3 is less than 1, which means ln of 2/3 is actually less than 0. Which makes sense because you want this to get smaller so that the temperature actually gets bigger, right? But because k is less than 0, if you actually are to pass to a limit in the sense of think about what happens if as t goes larger, your function is going to look like this. It's going to be a decreasing function, an exponential function. The limit will be 0, right? So the idea is that this is going to go to 0, so your limiting value would be 20, which obviously, as I said, makes sense, because if you leave the drink long enough in the room, it will be the temperature of the room, right? Is that making sense? Okay. So, part B says, when will the temperature be 15 degrees? I'm assuming you know how to solve that by now, right? You say 15 equal to, 20 minus 15 e to the k times t, and you have to solve for t, right? We've done these problems before. Let's show. Okay. The last topic of the section is compounded interest. And I've kind of briefly mentioned that when we looked at the definition of E, right? But the way it works is that A of t is the amount after at time t. And A of t is given by A0 times 1 plus R over N to the NT. This is the amount of money at time t where A0 is the initial investment, R is the yearly interest rate, and N is the amount number of times interest is compounded per year. So you could have it, monthly compounded, yearly compounded, bi-monthly, bi-yearly, or any other combination. You've seen this before, I'm guessing, right? More or less. So one of the problems you're going to have is going to be, one of the problems from the homework is number 18. It says if $500 is borrowed at 14% interest, find the amounts due at the end of 2 years if the interest is compounded, number 1, annually, number 2, quarterly, number 3, monthly, number 4, daily, number 5, hourly, and number 6, continuously. So the only thing we haven't talked about is continuously. How do we get to continuous compounding? Well, if n is the number of times you compound a year, then it only makes sense that n will go to infinity. Does that make sense? Yeah? Obviously, hourly is pretty much as continuously, if you think about the numbers, right? Because you have 256 days, 366 days, and you multiply that by, well, depends, I guess if it's a leap year or not. 365 times 24 hours, right? So it'll get like quite a large number, right? Okay. So how do we figure out what A of t is? Well, it's the limit as n goes to infinity of the quantity A0 times 1 plus R over N to the NT. Right? Yes? So what is that limit? So first of all, notice that A0 doesn't depend on anything. It's a constant, right? So I can take that out. Moreover, what I can do is I can write this as times the limit as n goes to 0 to infinity of 1 plus R over N to the N all raised to the T power.
Oh, wait, so if it's a constant, you can just completely move it out of the limit?
So far so good? Now would you know what that limit is? A0 times the limit as n goes to infinity, and what I'm going to do is the following. 1 plus R over N to the power, we'll write it in red over here. No, actually let me do this. N divided by R multiplied by R all to the T power. Is it the same as that? If you cancel out the R's, you come back with the previous one, right? But would you know what this particular limit is? It's E. And that's where we get to, well, PERT, but I guess they use A in this book. Does this make any sense?
No.
No?
I have no idea what you just did with the exponents.
Why is E the limit as n goes to infinity of 1 plus R over N to the N over R? Well, remember how we defined E. We defined it to be the limit as x goes to 0 of 1 plus x to the power 1 over x. Right? Well, as n goes to infinity, R is fixed. This quantity goes to 0. So if I define x to be R over N, all the way I will end up with 1 plus x to the power of 1 over x, which is exactly this. Okay? Wonderful. Questions? Do you know how to do problem 18 then? Obviously for continuously you need to use that formula. Yes? Okay. Then have fun with your beer experiments.